I'm Charles Pooh, Manager of Discrete Computation at Wolfram Research, and I will be presenting the new advance in number theory. Well, I'm Charles Pooh, and I will give you an overview of advance, I will say future advance in number theory. So essentially, in this talk, what I plan to do is just to give you an overview of what we are doing and kind of show you a concrete case. So we are trying to kind of revamp our number theory, right? And our approach essentially is first we want to improve usability. So that means documentation, and I will show you what we already did. So if you get there in our page, it's easy to learn, you understand the function and such. But also, obviously, we want to improve the algorithm. We want to, extend the scope. We want to have the state of the art, the fastest, the best. Right? So that's also in plan. And obviously, we want the performance, so the fastest. So what I will try to do is just to kind of give you an idea and show you a couple of examples how we plan to do that. And hopefully in the next couple of releases, we'll update most of the function, hopefully. So first, in terms of usability, and in this case, I will probably talk about prime pi. What we first think, we break usability in two parts, right? There's first the ease of use, and there is also the learnability. So first, for the learnability is more the documentation, is where, when you're a user, you have access to the function. So in this case, what we did is, unfortunately, I haven't yet it formatted on the new, it's not yet in the build, but I will try to enhance that. So what we've tried to do is first to improve the basic data. So if you have the earlier version, you can actually open it and see the difference. So in this case, we kind of try to, to tell you, give you the definition, the most natural one. None has also, so something which is similar. Define you the scope of the function, try to give you an idea of the function. So this one, well, the best thing you can do is, roughly speaking, give an asymptotic expansion. And something visual, so something has to look nice in that page. So in this case, we kind of show you that is kind of controlled by those. And as usual, we have the method option. So in this case, we introduce method option. This is I'm not a big fan of method option. So automation is fine. And like in this case, right, we know the best algorithm, usually you just run it. But for this type of function, some people like to use, old algorithm or compare. So what we did here, we exposed the standard algorithm from the lemma to the Lagrange-Miller and such algorithm, so you can actually specify them and then run them. And I will also probably also explain more about the progress reporting, which is part of the ease of use of the function. So that's kind of the detail that we are improving. So we changed it for, I believe, 70 or more of number theory functions. So that has been a whole project we have been going to improve all of them. And after that, you have the basic example. So we try to be sample, an idea, a nice visualization. And in this case, we show you that asymptotic. You can actually get the asymptotic expansion. Right. I will probably not, I was planning to talk about asymptotic, especially the relation with analytic number theory for this talk, but I will keep it for next time. Davendra will come next, and probably will talk about it and show nice example how you can compute asymptotic on number theory functions. And well, after that, you have the scope. So we broke the scope into numerical evaluation. Obviously, there's always a numerical evaluation for functions. So we show you the scope over integer, over rational number, and such. And we have symbolic manipulation. So which function can handle it, so kind of to show the scope and such. So you take it, you fit it to integrator, you fit it to find sequence function, can we recognize it and such. So we kind of try to show you the scope. And that kind of show you the integration of that function inside the language. And well, next, what we try to do, so I will jump the rest, we try to put a lot of examples to kind of, we try to give you that intuition builder. When you open the documentation page, you kind of get an idea of what's prime pi. So a lot of visualization, a lot of examples, from basic table to spiral of prime pi and such, so you have nice visualization to just learn what's the function and get an intuition. And after that, we have, in this case, approximation. Right? So if you get more in the hard code part, you know how you can approximate it from Riemann R and such. And the last part is about number theory. So there, strangely, it opened from the bottom. Okay, let me switch back. Nope. Well, the number theory, like in this case, we show you how you can use it to compute twin prime and such. And essentially, it's kind of give you an idea how you can construct it. So that's kind of pretty much the idea about the learnability. So our plan essentially is, to improve the documentation, and it's going to be in 12.1. And we hope that in the future version, we'll extend it to other related number theory functions, as well as probably write a course so people get more introduced to that. And the next part is actually the ease of use. One typical thing is when you have a function like that and we make it fast and such, you want to be able to control it, interrupt it, control the memory allocation and all this stuff. So we kind of improve it. And in this case, as I was showing there, PrimePy, we introduce a progress reporting, tentatively function. So you can get actually a progress bar to get an idea of the progress of the algorithm. We have to do the magic. So well, it depends on the function, right? So usually it's roughly an estimate, right? So there is two things, like in this progress reporting, right? You first have to be able to stop it, right? Especially like in the case of PrimePy, right? It was multi-threaded. You need to be able to exit correctly without any issue, right? And fast enough. And for the time, it's roughly an estimate. It's kind of what we rely on. So we know roughly asymptotically the time the algorithm can run. We run a couple of examples, and then we find a rough formula to give you an estimate. So it's more that perception as a user that something is happening, right? Currently, if you type PrimePy of, well, if you do PrimePy of 13, as I will show you, will tell you that it's too large. But in principle, if you run something, it will just, roughly speaking, hang. Some people say, all right, it hung, I'm waiting, nothing happened, right? So this is just to make you that feeling that something is happening. It doesn't have to be exact, right? And, well, let's actually show you a case, right? So, well, I will show you a case first. Well, I will jump to the next part, which is the scope, and I will show you the example. So in terms of scope, what we first try to improve is the ability of PrimePy to go above 10 to the 13. Or no, 10 to the 14 in this case. Right. So as you know, if you evaluate this in version 12, it will tell you, well, it's too large for this implementation. Right. So in the current version, you evaluate it, you will get that value. Right. And you can go higher, essentially. So let's see. So in this case, if you do progress reporting, goes to true. So you get the nice bar, and then, well, in this case, it's fast enough that you don't see it, but let's suppose 16. Right. So you have so roughly we try to estimate and do something. It doesn't have to be really exact. So that's kind of roughly the idea. But we hope that we should be able to give some rough estimate for each algorithm depending on the level. Right? And in the case of PrimePy, essentially, since we use the LMO, you know actually that you are computing for this number of leaves and such, so you have roughly the estimate of that. So in terms of scope, like PrimePy, well, we improve it. So roughly now is the state of the art. So, and currently you can get to 10 to the 27 or 10 to the 30. Right? So there's no more that limit. After that, you just, well, wait, I don't know how long to get that. But you'll get that progress report, and you should be able to actually stop it. And the algorithm is multi-threaded. It has all the nice, fancy feature, and fast enough. Okay, so here actually I kind of give an idea of the performance. There's pretty much nothing to argue about the plot there. So you see, roughly speaking, at the beginning, well, plus or minus, they are pretty close. But as you go to larger number, well, 12 pretty much hang or go to infinity. So that's pretty much it. So that's a great improvement we are kind of happy about. And here is just kind of the comparison between the automatic method as well as if you use a custom method like the Legendre method. So you see the difference. Okay. And obviously, if you implement prime_pi, you will get prime, right? Because roughly speaking, you need prime_pi to compute prime. So it's roughly computation of prime_pi and then sieving. Right? So also there we kind of cross that limit. So prime also have that limit on n, which was 2 to the, it was twice that number, 10 to the 13. Right. So now you can actually go higher and get it efficiently, hopefully. Well, it's computing. Right. But you can actually cross that limit. I'm surprised that's taking that much. Right. You will get back at some point. So we have those improvements for all the prime function, prime_pi, prime, and as well as, well, I about it, right? As well as, random prime, right? So essentially, what we discover is if you implement essentially prime_pi fast enough, you pretty much get improvement for all those functions. So random prime, essentially, you want to, sample prime following a certain distribution. So hopefully something uniform, right? So this is kind of the standard algorithm. If you want to get it uniform, you just compute prime_pi, right, plus or minus 1 here. Compute prime_pi, select the numbers, and then use prime to come back. So there you get exactly the uniform distribution. Right? And when the number gets extremely large, well, then there you just use the trivial algorithm where you essentially sample an odd integer and check if it's prime q. So, and that one is close to uniform. So it's a statistical distance from uniform. So having prime_pi, you also have a performance improvement on random prime. And actually, up to the 10 to the 13, I think that's the bound we change now, you actually get exactly uniform. So we sample actually exactly. So which is actually good, so we can actually document that. Okay, so, well, I want to kind of roughly give an idea of where we are essentially going, and we hope actually to improve those functions. So one is essentially look at what's the state of the art, what people actually build, right? So when we have it, one of the things we notice essentially is that we can take advantage of having a fixed width integer type, because usually in number theory, all the algorithms play on dispatching based on the size of the number. Most of the time. Right. I should correct that, Mark. I saw your face, but yes. So, and based on that, essentially, you can focus on a specific implementation and dispatch to that implementation. So it's what's happened with prime_pi now, and we think that, we started to do the same for factor integer. So like in the case of factor integer for the quadratic sieve, right, we know roughly the limit. The quadratic sieve currently is the best up to the 100 decimals. Right? So that means you have a fixed size integer type you can focus on. And if you make your implementation fast enough, multi-threaded, you get all the benefit. So that's kind of our plan. Essentially, we find the best algorithm. We work on a fixed type. We make it multi-threaded. And we make sure to dispatch and to know the right bound. Right. And lately with when we actually rewrote prime q, roughly based on that same principle, using the strong looker test, both strong and weak looker test. And you can actually also get that performance, at least 50% improvement in running time. So that's kind of the general plan we are going, and we'll just push in that direction. So I will not really push and bore you with all the technicality behind. So if anyone have question about how we manage to tweak it or do some multi-threading, well, feel free to catch me later. So that's pretty much the general overview I wanted to give about number theory. Thank you.